So I want you to imagine a scenario straight out of Carl Sagan's novel, Contact, the 1985 one.
Oh, right, yeah. Such a classic.
It really is. And in the climax of that story, the scientists are crunching the infinite digits of pi. And deep inside the base 11 expansion of those numbers, they find a message.
Right, and it's not just, random noise that looks like a message if you squint.
Exactly. It's a clear, undeniable geometric signal, which is just a brilliant science fiction concept. But it immediately poses this massive real-world problem for us.
Yeah, a huge one.
Right, like if we actually found a hidden structure in pi today, how could we mathematically prove it was put there by an alien intelligence and not just, a completely random coincidence?
I mean, it is the ultimate needle in a haystack problem.
Right.
Except the haystack is literally infinite.
Right.
And the dilemma isn't just about building a computer powerful enough to find the needle. The real obstacle is proving the needle isn't just a normal piece of hay that you accidentally convinced yourself looked sharp.
Yeah.
Because before we can even begin to talk about non-human intelligence or embedded cosmic messages, we really have to confront the flaws of our own brains.
Yeah.
And the primary hurdle here is this famous cognitive bias called the Texas sharpshooter fallacy.
I absolutely love the imagery of this one.
It's great, right?
It's so good. It's this apocryphal story of a gunman who fires his revolver wildly at the side of a barn. Just totally random shots.
Right, just blasting away.
Yeah. And afterward, he walks up to the wood, finds the tightest cluster of bullet holes, and paints a bullseye right around them.
So to anyone walking by, he looks like a master marksman.
Exactly. But the pattern wasn't deliberate at all. It was artificially isolated after the fact.
Yeah.
And when we talk about pi, I mean, a number with infinite deterministic digits, this is a terrifying problem.
Yeah.
Given an infinite string of numbers, couldn't we find absolutely any pattern if we just look hard enough?
Oh, easily.
Right. Couldn't we just paint a target around random noise and declare, hey, we found an alien message?
We absolutely could,
Yeah.
and we probably would.
Okay, so let's unpack this, because today we are embarking on a deep dive into what is basically the absolute limit case of human pattern recognition.
Yeah, it's a dense one.
It is. Our source for this deep dive is a rigorously mind-bending dissertation on the, quote, epistemology of mathematical design detection.
Such a mouthful, but so fascinating.
Truly. And our mission today is to bridge Diophantine geometry, computational complexity, and the search for non-human intelligence. All to give you, the listener, a definitive framework for separating deliberate design from natural coincidence.
Which is quite the goal.
It is. But to understand how we search for patterns, we first have to understand the canvas we are searching on. We need to talk about pi itself.
Which honestly is much trickier than it sounds.
Yeah.
Because pi is a transcendental number. That's a property proven way back in 1882 by the mathematician Ferdinand von Lindemann.
Right, 1882. So what does being transcendental actually mean in this context?
So being transcendental means its digits aren't generated by any finite algebraic process. Like you cannot simply set up a polynomial equation with integers, solve for x, and get pi.
Oh, I see.
It just defies that kind of finite algebraic generation. Yet, ironically, its digits are completely 100% determined by the basic unchangeable geometry of a circle.
So it's mathematically fixed.
Oh, yeah, that's right.
Meaning if you find a pattern in pi, you didn't invent it. It was always sitting there waiting to be found.
Yes, exactly.
But for the longest time, looking for those patterns was kind of like trying to read a never-ending book and being forced to start from page 1 forever.
Right, you had to compute digit number 1 to figure out digit number 2.
Yeah, and you'd have to compute digit a billion to get digit a billion and one. It was entirely sequential.
It was, until 1995.
Right, in 1995, mathematics gets this massive breakthrough, the BBP formula.
Yes, named after Bailey, Borwein, and Plouffe.
And this formula fundamentally revolutionized how we interact with transcendental constants, right?
It absolutely did. In computer science, it is what's known as a spigot algorithm.
Which basically acts like a magical index for that infinite book.
Exactly.
Because it allows us to compute the nth digit of pi without computing any of the preceding digits. We can just jump straight to, say, the trillionth digit.
Yep. And the formula does this incredibly fast. It scales in what computer scientists call big O of n, log cubed n time.
Okay, wait, what does that mean in plain English?
It basically means the computational effort doesn't spiral out of control as you jump further down the number line. It stays efficient.
Oh, wow. Okay.
But there is a catch.
There's always a catch.
Right. The BBP formula gives us what the dissertation calls base 16 privilege.
Base 16 privilege.
Yeah, meaning the algorithm is optimal, but only if you were calculating pi in hexadecimal.
Ah,
And
okay.
this was a profound revelation because it proved that pi possesses this unexpected algorithmic structure beyond just, spitting out digits one by one.
It has a hidden architecture.
Yes, an architecture that we can exploit to navigate it.
But wait, I have to push back on this a little bit.
Sure, go ahead.
Pi is just a number, right? It's just the ratio of a circle's circumference to its diameter.
True.
So if we change the base, like looking at it in our standard base 10 versus base 16, doesn't that just change how we're looking at it?
Huh.
Like it doesn't change the underlying number itself, does it?
So what's fascinating here is the vital distinction between ontology and epistemology.
Okay, big words. Break that down for me.
Right, so the number itself, the ontology, the physical reality of what pi actually is, that is absolutely base independent.
Okay.
Think of the famous Ulam spiral of prime numbers.
Oh, I've seen that, where you arrange numbers in a spiral and the prime numbers line up on those strange diagonal sequences.
Exactly. That geometric reality exists regardless of whether you write the numbers in English, binary, or Roman numerals.
Right. The primes are still primes.
Exactly.
Yeah.
But our epistemology, our actual ability to recognize and extract a pattern that is highly dependent on the base we use.
Oh, I get it now.
Yeah, so the BBP formula matters because it bridges the analytic universal truth of pi with our specific digital representation of it.
That makes so much sense.
Yeah.
So pi has these hidden mathematical structures that we can jump to, provided we use the right lens, like hexadecimal.
Precisely.
But that brings us directly to the next massive hurdle.
The sharpshooters.
Exactly. Because if we use this magical index, jump to a random spot, a trillion digits deep, and find a highly complex pattern, how do we prove that structure is actually rare? How do we prove we aren't just being Texas sharpshooters painting a target around a random cluster of maths?
Well, to solve that, the dissertation argues we have to pull in tools from an entirely different field of mathematics, Diophantine geometry.
Now, if you are listening to this, you might be wondering how a field that deals with geometric curves and polynomial equations applies to a straight list of decimals.
It does sound like a stretch.
Yeah. Mapping a continuous geometric curve to the discrete digits of pi sounds wild.
It sounds totally impossible until you look at the mechanics of it.
So how does it work?
Imagine taking blocks of pi's digits and treating them as the x and y coordinates on a graph, or as the coefficients in a polynomial equation.
Okay, I'm visualizing that.
You are essentially taking the sequence of pi and asking, if this sequence were a location on a specific algebraic curve, would it be a valid point?
Oh, wow.
And in Diophantine geometry, the central problems are all about constraints. Does a solution exist? Are there finitely many solutions?
Because to stop the Texas sharpshooter, we need mathematical limits.
Exactly. We need boundaries. And the ultimate limit arrived in 1983 when Gerd Faltings proved the Mordell conjecture.
Okay, let's break down the mechanics of this Mordell conjecture, because this is crucial.
It really is. So Faltings proved that certain algebraic curves, specifically those of genus 2 or higher, have finitely many rational points.
Genus 2, let's visualize that. Genus basically means the number of holes in a shape, right?
Yep, exactly. A sphere is genus 0. A donut is genus 1.
And a figure-8 donut with 2 holes is genus 2.
Spot on. Faltings proved that once a curve hits that topological complexity of 2 or more holes, the number of rational coordinates that can neatly map onto it stops being infinite.
It stops being infinite.
Yes. This introduces what the author calls finiteness as epistemic closure.
Finiteness as epistemic closure. I love that phrase so much.
It's very poetic for math.
It is.
Yeah.
And translated out of the math, it basically means there is a hard mathematical ceiling on what can exist.
Right.
You can search the infinite digits of pi forever, but you will not find infinitely many complex points mapping to these curves.
Exactly.
We can think of this as a strict complexity budget. Faltings proves that this budget exists, meaning there's a limit to how many complex patterns can just randomly appear by chance.
But, and this is a big but, Faltings' proof had a really frustrating quirk.
Right, because it was an ineffective proof.
Yes, ineffective. In mathematics, an ineffective proof tells you that something is absolutely true but gives you no tools to measure it.
So Faltings proved that only a finite number of points exist, but his math didn't tell you where they were or what the absolute maximal number was.
Right. It's like knowing there's a spending limit on your credit card, but the bank absolutely refuses to tell you what the actual dollar amount is.
Which is completely useless when you're actively hunting for anomalies.
Totally useless. You don't know when you've broken the budget.
See, so how did we fix that?
Well, mathematicians recognize that gap.
Yeah.
Enter the work of Trobody and Coleman.
Okay.
They developed effective methods. Through advanced calculus on these curves, they generated computable bounds. They basically gave us the exact dollar amount of the complexity budget.
Amazing. But the framework goes even deeper than that, doesn't it?
It does.
Because when those simple bounds fail to capture the whole picture, the math brings in concepts like quadratic Shabadi and Kim's non-abelian Shabadi.
Yeah, and those concepts address a much deeper layer of coincidence.
Like what?
Like, what do you do when a pattern's individual complexity doesn't seem that rare, but its placement is highly suspicious?
Oh, I see.
Quadratic and non-abelian Shabadi measure higher-order correlations.
Yeah.
They calculate the mutual information between a pattern and its exact spatial location.
So it's the mathematical equivalent of saying, this pattern is somewhat complex, but the fact that it appears exactly at this specific junction requires a massive coordinated amount of mathematical machinery.
Exactly. It's the context that makes it impossible by chance.
Okay, so we have our complexity budget. We have the Chirati bounds to calculate exactly how much coincidence the universe naturally tolerates.
Right.
But what happens when a pattern shatters the budget? Like, what if we find something vastly more complex than the Chirati bounds say should naturally exist in that location?
That's the million-dollar question.
Right. How do we know it's not just the natural laws of math doing something weird we just don't understand yet?
To rule out natural math, we introduce the concept of modular forms and the Akin-Leonard test.
Okay, more new terms.
Yeah, stick with me. In this framework, we start treating the different bases of pi, so base 10, base 16, base 2, as different levels in a grand modular hierarchy.
Okay.
Modular forms are these highly symmetric, complex functions that map out the deep relationships between numbers.
Let me see if I can put a metaphor to this just to make sure I'm tracking.
Go for it.
Think of an underlying pattern, like a melody. If you transpose a melody from C major to G major, the literal notes change, but the intervals, the underlying song, stay exactly the same.
Yes, exactly.
And if it sounds like beautiful music in C major, but turns into completely random noise when you transpose it to G major, then it wasn't a natural, mathematically pure song to begin with.
Right.
It was just a coincidence of the original key.
That is a perfect analogy. If a pattern in pi is a naturally occurring mathematical structure, it must respect that hierarchy.
It has to survive the transposition.
Precisely. It should transform coherently when we test it with Akin-Leonard involutions, which are essentially mathematical rotation operators that shift our perspective.
Wow, okay.
A natural pattern must satisfy what are called Heck relations, maintaining its structural integrity, no matter the mathematical angle we view it from.
So it's robust.
Very. And to put this into practice, the dissertation proposes a three-tier Kolmogorov-Chibadi sieve.
A three-tier sieve to filter out the Texas sharpshooters' fake targets once and for all.
That's the idea.
Let's walk through the mechanics of this sieve.
Okay, Tier 1 tests local bases. It checks if the pattern remains structurally consistent across multiple representations, like jumping from binary to hexadecimal.
Checking if it survives the key change.
Exactly. Tier 2 looks for global intersections. This eliminates ghost patterns, which are basically mirages that only exist as a fleeting artifact of one highly specific way of slicing the numbers.
Makes sense. And the final tier.
Tier 3 is the ultimate check. It verifies the pattern against the complexity height budget using time-bounded Kolmogorov complexity.
Which is known as PKT, right?
Yes, PKT.
Now, standard Kolmogorov complexity just measures the shortest possible computer program you would need to generate a specific pattern.
Right.
But PKT adds a real-world constraint, doesn't it?
It does. It factors in time. Because a pattern might have a shortcode, but if it takes a computer longer than the age of the universe to run that code and produce the pattern, it isn't a naturally viable structure.
Oh, wow. So PKT measures both the brevity of the code and the efficiency of generating it.
Exactly.
Okay, here's where it gets really interesting.
Yeah.
Let's play devil's advocate for a second.
Okay.
I run a suspicious pattern through this extremely rigorous three-tier sieve, and it survives.
Okay.
Is it still mathematically possible that I just got incredibly lucky? Like, that I hit a sharpshooter anomaly that perfectly mimics a design message by sheer random chance?
So if we connect this to the bigger picture, you have to remember that mathematics imposes rigid, inescapable laws.
Right.
If a pattern survives the three-tier sieve, meaning it is extraordinarily rare and complex, but it fails the Akin-Leonard symmetry test, we have our answer.
Because failing that test means the pattern lacks natural mathematical symmetry.
Exactly.
Mm-hmm.
It doesn't transform coherently like your transposed melody.
Yeah.
If a pattern is wildly complex, but structurally unnatural, it is mathematically impossible for it to be a random anomaly.
Because natural anomalies follow natural geometry, so
Right.
if it doesn't follow the geometry, it's deliberate.
The laws of finiteness simply don't allow for an anomaly of that magnitude without underlying natural symmetry. It has to be designed.
That is just
It
mind-blowing.
really is a solid framework.
Let's pull this abstract framework down to earth and actually apply it. Because the source text tests this epistemological sieve against 3 hypothetical discoveries hidden in pi.
Yes, the scenarios.
Right. What if we actually found these things? Scenario A is Gödelian self-reference. What does that actually look like mathematically?
Okay, imagine finding a string of numbers in pi that essentially acts like a self-extracting archive.
Like a zip file.
Yeah, exactly. The pattern encodes the very digit index where it is located. It says, I'm a pattern, and I am located at digit number 42 billion.
That's creepy.
It is. And furthermore, it contains internal checksums, like mathematical verification codes, to prove its own structural integrity. It knows exactly where it is,
It's a self-aware sequence of numbers.
basically.
So how does the framework judge it?
We apply the Atkin-Lehner transformation. We transpose the melody.
Okay.
If this self-referential pattern survives the transformation, meaning it scales coherently into different coordinates and the checksums still balance out,
Yeah.
then it's a profoundly weird but entirely natural mathematical law of the universe.
Wow.
However, if the pattern is totally coordinate dependent, like if shifting the mathematical perspective completely breaks its internal logic.
Then it lacks natural symmetry. It's
Right.
a localized artificial design.
Exactly.
But self-reference is just one flavor of anomaly. What if the pattern is actively doing something useful, like in scenario B, error-correcting codes?
Right.
What if we find a pattern with a Reed-Solomon or Hemming code structure?
Well, those are the exact algorithms we use in human telecommunications and like deep space probes to prevent data corruption.
Right.
Now, we must be careful because nature does utilize error correction.
Like DNA repair mechanisms.
Exactly. But natural error correction is usually just, good enough. It relies on brute force physical redundancy, just making tons of copies of the data.
Okay.
Human-engineered codes, however, strive to be what mathematicians call singleton-bound optimal.
Singleton bound meaning the absolute maximum possible error correction achieved with the minimum possible data overhead.
Right. It is mathematically perfect efficiency.
Which nature doesn't usually do.
No, it is an optimization that nature just doesn't bother with. Now, the text notes that mathematical constants do feature some self-correcting algorithms like Borvine's cubic methods, but those exist to correct our computational approximations of pi, not the physical sequence of the digits themselves.
Ah, I see the distinction.
Right. So if we discover a singleton-bound optimal error-correcting code deeply embedded in the digits, and it actually functions to correct digit extraction errors.
That degree of optimal non-physical redundancy is a massive signature of intelligent design.
It would be a smoking gun.
Incredible. And then there is the third hypothetical, the one that completely upends everything. Scenario C, the Sudoku paradox.
Yes, this one is wild.
It is. Let's say we are scanning the very first 200 digits of pi. We aren't jumping trillions of digits deep. This is universally accessible to a kid with a calculator.
Right.
And embedded seamlessly in those first 200 digits, we find a perfectly valid, solvable 9x9 Sudoku puzzle.
Yeah, and the statistical probability of a valid 9x9 Sudoku grid naturally occurring in a random sequence of numbers is roughly 10 to the negative 56 power.
So basically 0.
It is practically indistinguishable from 0, yes.
So what does this all mean? We find a human puzzle, a game with a 9x9 grid that became popular in Sunday newspapers in the 1980s, sitting right at the front door of a universal mathematical constant.
Sounds absurd.
My immediate reaction reading that was complete skepticism. Wouldn't hyper-advanced alien intelligence use elegant universal math?
You think so?
Why would a godlike species leave us a base 10 human game? It sounds like an obvious hoax.
And that skeptical intuition is precisely what the Kolmogorov-Chibody framework is built to evaluate.
Okay, so how does it handle the Sudoku?
The framework introduces the concept of an interface layer. Let's run the Sudoku through the rigorous tests. Does it possess any deep modular structure? No.
None at all.
Does it exhibit Atkin-Lehner symmetry when we shift mathematical bases? 0.
Right.
It entirely ignores the natural mathematical hierarchy of the universe. Furthermore, as you pointed out, It is hyper-specific to human cognition.
Yeah.
It relies exclusively on base 10 digits and a 9 by 9 grid, which are human cultural artifacts.
It's basically speaking our messy, localized language.
Exactly. And here is the crucial synthesis.
Mhm.
Because it requires absolutely zero computational search effort, sitting plainly in the first 200 digits, it doesn't break the complexity budget through deep data mining.
Right, there's no sharpshooter fallacy because we didn't have to search a trillion digits to find it.
Right, but because it wildly violates all natural mathematical symmetries, the framework dictates it cannot be a mirage created by the Texas sharpshooter.
Oh, I see.
It is an interface layer. It was rendered accessible specifically for our human cognitive constraints. The lack of natural symmetry is the proof.
Wow.
Finding that Sudoku would be irrefutable, mathematically verifiable proof of external intelligence.
Because the designer deliberately ignored the elegant modular structure of universal mathematics to drop a puzzle on our front porch in a format we couldn't possibly miss.
Exactly.
Wow. Okay, so let's recap this incredible journey. We started with the ultimate Texas sharpshooter question. Can you find anything in an infinite string of numbers if you look hard enough?
And thanks to this rigorous epistemological framework, the answer is a definitive, resounding no.
Right. Mathematical reality is not just a blank, infinite canvas where any random noise can be justified as a meaningful pattern.
No, the constraints of the universe are real and they are measurable. Finiteness, computable bounds, and natural geometric symmetries dictate exactly what is allowed to exist by chance.
You have a strict complexity budget.
Exactly. And if a pattern shatters that budget and completely breaks the rules of natural symmetry to do so, it is deliberate.
It's so vital to remember the mechanics of this, not just for hunting hypothetical alien messages, but for navigating our daily lives.
Oh, absolutely. I
Yeah.
mean, we currently live in an era defined by unprecedented information overload. False pattern recognition is everywhere you look.
He really is.
We see it in conspiracy theories that try to connect entirely unrelated data points by ignoring the broader context. We see it in AI systems hallucinating patterns in data that simply aren't there.
Yeah, that happens all the time now.
Applying this concept of a complexity budget and testing for natural symmetry isn't just a party trick for number theorists. It is a vital, everyday, critical thinking tool.
So true.
If someone shows you a miraculous pattern, ask yourself, does this structure survive a shift in perspective? Does it hold up when I change the parameters? Or is it entirely dependent on the highly specific, artificial way they've chosen to present the data?
Are they just painting a target around random bullet holes? There's one final, provocative thought from the source's future directions that I want to leave you with. It's something for you to really mull over until our next deep dive.
Oh, this part is wild.
It is. If someone or something did manage to design a message and embed it into pi, an immutable mathematical constant that is baked into the very foundational definition of a circle, what does that imply about the geometry of our spacetime?
It is a staggering philosophical implication.
It really is. Because if the fundamental digits of pi can be intentionally manipulated, then the concept of the circle itself is an artifact.
Yeah.
Is the universe itself just a constructed interface? Did the author of that hypothetical message not just write words on the paper, but invent the very concept of paper to begin with?
Mind-bending.
Keep that in mind the next time you look at the stars or, try to solve a Sunday Sudoku puzzle.